This lecture is going to talk about reading and writing data in R. So there's a few different types of ways you can do this, and I'm going to talk about some of the primary functions that you use in R to read and write data. So there are a few principal functions that we're going to talk about for reading data into R. First two are read.table and read.csv. And these are for reading tabular data, and they're probably two of the most commonly used functions for reading data into R. These functions read text files that contain data that are stored in kind of rows and columns type of format and return a data frame in R. The function readLines is for reading lines of a text file, and so this can read any type of file really. It just gives you text in it as a character vector in R. The source function is important for reading R code. So if you have a R code, for example, functions or anything written to a file, the source function will read all that code into R. The dget function is also for reading R code files, but it's for reading R objects that have been what are called deparsed into text files. We'll talk a little bit more about this later. The load and the unserialized functions are for reading binary objects into R. So the analogous functions for writing data are write.table, writelines, dump, dput, save, and serialize, and those kind of pair up with their reading analog. So the read.table function is the most commonly used function for reading data into R. And it's important that you know kind of how the arguments work, what the arguments are, and understand what they mean. So the first argument is pretty obvious. It's the name of a file or the name of a connection, which we'll get to a little bit later. Usually you're going to give this a file name. It's going to be a string, and it's going to be a path to a certain file in your computer. The header is a logical flag indicating whether the first line is a header line. So if the first line, for example, it has all the variable names in it, then that's not really a piece of data. That's just a line that has labels on it. So you want to tell the read.table function whether the first line contains the variable names or not, or whether the first line just right away contains data. The sep argument stands for separator. It's a string that indicates how the columns are separated. So, for example, if you have a file that's separated by commas, then the separator is a comma. Sometimes files are separated by semicolons or by tabs or by spaces, and so you want to tell read.table what the separator is going to be. Call classes is a character vector whose length is the same length as the number of columns in the dataset, and the character vector indicates what is the class of each column in the dataset. So, for example, if the first column is numeric, and the second column is logical, and the third column is a factor, etc. And so the call class is a vector, which is not required, but it tells read.table what the class of the data is for each column. Nrows is the number of rows in the dataset. This is not required, but it can be used. Comment.char is the character string that indicates what's the comment character. So the default, for example, is the pound symbol or the sharp symbol, and anything to the right of that symbol is ignored. It's the comment character. So you can specify other characters to be comment characters, and the lines of the file that begin with that comment character will be ignored. Skip is the number of lines to skip from the beginning. So sometimes there may be some header information or some non-data region at the beginning of the file, and you want to skip right over that. And so you can tell the read.table function to skip, say, the first 10 lines or the first 100 lines, and then only start reading data after that. The last argument is strings as factors. This defaults to true, and the idea is that the question is whether you want to encode character variables as factors. So by default, anytime our read.table encounters a column of data that looks like it's a character variable, it will assume that what you mean to read in is a factor variable. If you don't mean to read this in as a factor variable, then you can set strings as factors equal to false. So for small and kind of moderately sized data sets, and as computers kind of get better and better every day, the definition of small and moderate is kind of growing. But you can use read.table usually without specifying any of the other arguments besides the file name. So you can say read.table on, say, foo.txt. So this is just the name of the file, and it will automatically take care of figuring out what the classes of the different columns are. It will figure out how many rows there are, etc. So you don't have to specify any of that information if you don't feel like it. And then this will return an object here that I call data, and that will be a data frame. So it'll automatically skip any lines that begin with the comment symbol. It will figure out how many rows there are, and again, it'll figure out what type of variable is in each column of the table. So you can tell R all these things, and if you want to, and the reason you might do that is to make it run faster and more efficiently. So with small and moderate sized data sets, there's usually not much advantage to doing that because it'll be pretty fast and pretty efficient as it is. The read.csv function is identical to read.table, except for the key difference is that the default separator for the read.csv function is the comma, whereas the default separator for read.table is a space. So read.csv is useful for reading CSV files. These can usually be, so that stands for comma separated value. It's usually something that you get from a spreadsheet program like Microsoft Excel or something similar to that. So CSV is a very common format that most spreadsheet types of programs will understand. The other thing that read.csv specifies is that it always specifies header to be equal to true. So with larger data sets, so beyond the small to moderate, then there are a couple things that you can do when reading in tabular data that will make your life a lot easier, and also, and more importantly, will prevent R from totally choking. So first, you should read the help page for read.table. In fact, you should probably have it memorized. There's a lot of key hints in that help page and a lot of useful information. And in my opinion, not enough people read this help page carefully enough so that they can kind of recite it in their sleep. And so there's a lot of, so once you've read that, you'll see there's a lot of important information for kind of how to optimize read.table, in particular for large data sets. And so one of the things you're going to want to do is to make a very rough calculation of how much memory you need to store the data set you're about to read. And so in that way you can get a sense of, well, is there enough memory on my computer to store this data set? Because if you recall correctly, R is going to store your entire data set in memory unless you do otherwise. So when you call read.table or read.csv, it's reading your entire data set into the RAM of the computer. And so you need to know, roughly speaking, how much RAM this data set is going to require, and we'll talk about how to calculate that in a second. So another easy optimization you can say is if there's no comment lines in your file, then just set the comment.char argument to be blank. So just an empty quote there. The call classes argument is actually very important because if you don't specify it, then what R does by default is it goes through every column of your data set and tries to figure out what type of data it is. Now, that's all well and fine when my data set's small to moderate, but reading each of these columns and trying to figure out what type of data it is takes time, it takes memory, and it can generally slow things down. If you can tell R what type of data is in each column, then R doesn't have to spend the time to figure it out on its own. And so it'll generally make read.table run a lot faster. And so you can save yourself a lot of time. So if you have a few columns in your data set, then you can usually just say what the classes are. But if you have, if they're all the same, then so for example, if all the columns are numeric, you can just set call classes equal to numeric. And if you only give it a single value, it will just assume that every column has that same value. So if you just say numeric, it will assume that every column is numeric. Otherwise, what you can do, if you have a huge data set, you can read in maybe the first 100 or the first 1,000 rows by specifying the nRows argument, and then going through each of the looping over each of the columns using sapply and calling the class function. So the class function will tell you what class of data is in each column, and then you can use this, and then you can store this information and then read the entire data set by specifying the call classes argument. So the nRows argument is actually very useful too. It doesn't necessarily make R run any faster, but it does help with memory usage. And so if you can tell R how many rows are going to be read into R, then it can calculate the memory that's going to be required and not have to kind of figure it out on the go. So even if you mildly overestimate how many rows there are in the data set, that's okay because it won't make a difference. It'll still read the correct number of rows. So in general, when you're using R with large data sets, and there's lots of large data sets out there nowadays, it's useful to have a few things, just kind of a few bits of information on hand. So for example, how much memory does your computer have? How much physical RAM is there? These days, most computers will have on the order of a few gigabytes up to many gigabytes of physical RAM. What other applications are in use? So are there other applications that are running on your computer that may be eating up some processor time or memory? If you're on a multi-user system, are there other users logged into the system? Are they using up some of the resources on the computer? What is the operating system for your computer? So is it a Mac? Is it Windows? Is it Unix? Is it Linux? Is it something like that? And then also it's useful to know whether the operating system that you're running is 32-bit or 64-bit. On a 64-bit system, you'll generally be able to access more memory if the computer has a lot more memory. So if you want to do a rough calculation before you read in a table into R, using the read.table or the read.csv function, you can just do a very quick calculation. So here, suppose I have a data frame here with 1.5 million rows and 120 columns. So this is not a particularly big data set, but it's reasonable. And suppose that all the columns are numeric, so I don't have to worry about different types of data. All the columns are numeric. The question is, how much memory is required to store this data frame in memory? Okay, so I can do a simple calculation. So the number of elements in this data frame is going to be 1.5 million times 120, right? Because it's a square object, and so that's the number of elements in the data frame. Now, if it's a numeric, all the data are numeric, then each number requires 8 bytes of memory to store, because the numbers are stored using 64-bit numbers, and there's 8 bits per byte, so that's 8 bytes of memory per numeric object. So that's going to be, so here's the number of bytes. Now, there's 2 to the 20 bytes per megabyte. And so I can divide the number of bytes by 2 to the 20, and that's how many megabytes I got. So I've got 1,373.29 megabytes. And I can divide that again by 2 to the 10 to get the number of gigabytes, so it's going to be roughly 1.34 gigabytes. So the raw storage for this data frame is roughly 1.34 gigabytes. Now, you're actually going to need a little bit more memory than that to read the data in, because there's a little bit of overhead required for reading the data in. And so the rule of thumb is that you're going to need almost twice as much memory to read this data set into R using read.table than the object itself requires. So if your computer only has, let's say, 2 gigabytes of RAM, and you're trying to read in this 1.34 gigabyte table, you might want to think twice about trying to do it, because you're going to be pushing the boundaries of memory that is required to read this data set in. Of course, if your computer has like 4 or 8 or 16 gigabytes of RAM, then you should have no problem in terms of the memory requirements. It will still take some time just to read it in, just because it takes time to read in all the data, but you won't be running out of memory. So doing this kind of calculation is enormously useful when you're reading in large data sets, because it can give you a sense of, do I have enough memory? Is the reason, if you run into any errors, you'll know whether the error is because of memory, running out of memory, or not. So I encourage you to do this kind of calculation when you're going to be reading in large data sets, and you know in advance kind of how big it's going to be.